Ionization energy is a measure of how easy it is to remove an electron from an atom to form a positive ion, or even to remove an electron from a positive ion to form a more positive ion. You need to know the definition for first ionization energy. So the energy required to remove one electron from each atom in a mole of gaseous atoms of an element to form 1 mole of gaseous ions. And the units, as its energy, would be kilojoules per mole. It's really important to know your definitions, because if you're asked to write an equation to represent, for example, first ionization energy, you're going to get it right. So we could take lithium, for example. Lithium, it's a gas. If it loses an electron, we would form the positive ion plus the electron that had been removed. Now, if an atom or indeed an ion has got more than one electron, then we can work through our successive ionization energies. So the second ionization energy for lithium would be starting with the positively charged ion to form an ion with a 2+ charge, and so on. Please remember to use state symbols. That's always worth a mark in the exam. How easy it is to remove an electron from an atom depends on 3 simple things. Firstly, the atomic radius, which is the distance between the nucleus, that positively charged centre, and the electron being removed. The nuclear charge, or the number of protons in that nucleus, which gives us an idea of the amount of attraction, the degree of attraction between the nucleus and the electron being removed, and electron shielding. So I'm going to look at that in a little bit more detail. So let's take lithium, for example. Lithium has 3 protons. So we would have 3 protons in the nucleus, and then just working on the simple model of the atom with our electrons and shells, 2 electrons in the first shell and 1 in the second. Now clearly this electron here is going to be relatively easy to remove because it's quite far from the nucleus, and this is what we mean by electron shielding. These inner electrons are essentially blocking that positive nuclear charge. So the electron on the outside, the outermost electron, doesn't feel the full effect of 3 protons pulling it in. Clearly, if we were going to lose a second electron, so let's draw it out. So if we have lithium, it's not what I wanted to write at all. If we have lithium with its 3 protons, and it's an ion, if it's already lost an electron, so this is lithium plus, we can represent that with square brackets and a positive charge. First of all, it's important to note that now that we've lost an electron, these 3 protons are going to be attracting the 2 remaining electrons more strongly. So the distance between the nucleus and that first shell is going to be smaller in the lithium ion than it was in the lithium atom. They also have no shielding. So let's make a note of these 2 things. So distance is smaller and no shielding. So these electrons here would feel the full force of the 3 protons in the nucleus, which means it's going to be very difficult to remove them. We're going to need far more energy to remove an electron from the inner shell than we did the first electron from the outer shell. And we can see that really clearly if we look at the actual values for ionization energy. So what we're seeing here, if we look at lithium, it takes 520 kilojoules per mole to remove 1 electron from one atom, from each atom in a mole of atoms for lithium. And then it takes 7,298 to remove the second one for exactly the reasons we've just explained. With magnesium, we see a slightly different pattern. We see that the first and second electrons, we don't require that much energy to remove them compared with the third. So ionization energies are essentially our first piece of evidence that we can get our heads around at A level to back up our model of the atom, the fact that electrons are in shells, because the distance between electrons and different shells is represented by the amount of energy it takes to remove them from the atom. We can see that quite clearly if I look at magnesium. It's got 12 protons in the nucleus. I'm just using the very simple model of the atom. I can't even draw 3, 4, 5, 6, 7, 8, 10. So we've got 2. I should perhaps have drawn some circles beforehand, shouldn't I? We've got 2 electrons in our outer shell. So the amount of energy required to remove these 2 is considerably less than the amount of energy needed to remove an electron from the second shell, inner shell. Less shielding, closer to the nucleus. Those shells haven't been pulled in further anyway because the 2 outer electrons have been removed, and we've got a higher nuclear attraction there. So let's have a look at the trends in first ionization energy across the periodic table. The first one I want to look at is trends in the group. I've taken the noble gases here. Atomic number is along the bottom of this graph. We've got helium, neon and argon at the high points. Helium, neon, argon are all noble gases. They're in group 8. As we can see, as we go down the group, and this is the same for all of the groups, we see that the trend in first ionization energy is that it is decreasing as we go down the group. So why might this be? Well, let's have a look at our 3 atoms, which I've drawn out along the bottom here. We've got helium, neon and argon. As atoms, the number of protons and number of electrons is balanced, but first of all with helium we can see that the distance between the nucleus and the electron that we're removing, if we're going to remove the outermost electron, that one there, is much smaller. So we're going to have an increased nuclear attraction between those 2 protons and the outer shell electron, which means it's going to take more energy to remove it. And there are no inner electrons in helium. There is no shielding effect. Unlike if we have a look at argon, for example, not only have we got a greater distance between the 18 protons in the nucleus and the outer shell electrons, but we've got 2 inner shells worth of shielding. And that is more effective in determining the first ionization energy than the number of protons in the nucleus. So distance between the nucleus and the outer shell electron and the amount of shielding is kind of counteracting, more than counteracting, the fact that we have more protons in the nucleus. So let's have a look at the trend across a period. I've taken period 2 as my example, lithium through to neon, as we can see quite clearly from the graph. The general trend is that as we move along a period, the first ionization energy increases. Before we explain why, I'd like to address a common misconception. As we move along a period, the atomic radius, i.e. the size of the atom, the diameter, however you want to look at it, the atomic radius decreases. Why might that be? Well, the reason I hope you can see from the pictures that I've drawn below is that each time we add another electron to our atom as we move from one element to the next, that electron is going into the same shell. In the second period, it's the n equals to the second energy shell or energy level that that electron is being added to. At the same time, the number of protons is increasing. So our nuclear charge is increasing. The amount of shielding remains the same in each case. We've just got our 1s orbital in each of our atoms in the second period that has got 2 electrons in, so the amount of shielding remains the same. number of protons increases, and so we find a stronger attraction between the outermost electrons, or the second shell of electrons, and the protons. So the radius is getting smaller. Those energy levels are being pulled in towards the nucleus more strongly. As a result of that, it is going to take more energy to remove an outer shell electron. The first ionization energy is going to increase. If we take boron as an example again, we can see 5 protons, 5 electrons. Those electrons are closer to the nucleus. So we've got closer to nucleus because the atomic radius is smaller. We've got the same amount of shielding. If we add those two things together, then what we're actually seeing is greater nuclear attraction. And as a result of that, we've got a higher first ionization energy. And finally, let's have a look at this in a little bit more detail, because although in general the first ionization energy is increasing as we move along a period, we can see that there are a couple of blips. Beryllium to boron, nitrogen to oxygen. Well, based on what I've just said, surely boron should be higher than beryllium and oxygen should be higher than nitrogen, but it's not the case. Why might that be? I would encourage you very strongly to stop the video at this point and try and figure it out for yourself in terms of, and here's your clue, the detailed electron configuration for each of these elements. It's really important that you try to figure things out for yourself. Research shows quite clearly that we learn better, we remember more in the end if we've struggled to understand the reasons why. So me just telling you isn't going to be nearly as effective in the long term as you trying to figure it out yourself. So stop the video, have a think about it, then press go again. Detailed electron configuration. Well, let's have a look at beryllium. So beryllium has got 4 electrons. We can write them in terms of detailed: 1s, 2s. If we have a look at boron, we've got 5 electrons. Hopefully now you can already see what's going to happen. We've got our 2s. And then that 5th electron is actually going into one of the 2p suborbitals. And we know that the 2p suborbital is slightly further away. It has a slightly higher energy than the 2s orbital. So as a result of that, we're going to have a little bit of shielding from the 2s. In addition to it being slightly further away, it's going to make it slightly easier to remove it than perhaps we would at first think, hence the slightly lower first ionization energy. Let's do the same for nitrogen and oxygen. So if I look at nitrogen, nitrogen has got 7 electrons, so 1s, 2s, and here are my 2p orbitals. So 1, 2, 3, 4, 5, 6, 7. If you remember the rules, each of these electrons gets its own suborbital. That makes the lower energy more stable, minimises repulsion between them rather than having to spin pair. But oxygen does not have that luxury. So we're going to have the 1s, the 2s, I apologise, let me just and then the 2p. 1, 2, 3, 4. So with oxygen, that 4th electron is forced to spin pair. So we have got a little bit of repulsion, which means that it's going to be slightly easier to remove it than perhaps at first anticipated, hence the slightly lower first ionization energy as compared with nitrogen. So Once you've got your head around this in terms of understanding, I would really encourage you to go away and to rewrite, annotate your notes, use your textbook, use this video to help you so that you become confident in explaining it in your writing as well as thinking that you understand this. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the description below, it'll take you straight to Crunch Chemistry School, where you can access my free math skills course, complete tuition, and worksheets designed specifically to build your confidence and stretch you. Together we can do this.